We've seen that one important step, in fact the important step in computing a definite integral is to find an antiderivative. So that alone makes it very important for us to be able to construct antiderivatives, that is to find a formula of a function whose derivative is a function that we already know. So, because this process of finding an antiderivative is the inverse relation of the process of finding a derivative, say maybe by using our shortcut rules, we have, for every shortcut rule we have of finding derivatives, we have a corresponding antiderivative rule. So let's go over some of the most basic ones of those. So first of all, the sum rule. The derivative of sum is the sum of the derivatives. So guess what? That means the antiderivative of sum is the sum of the antiderivatives, and the definite integral of the sum is the sum of the definite integrals. The derivative of a constant times a function is a constant times that derivative function, so the constant can be brought out from the derivative sign. In a similar manner, the antiderivative of a constant times a function is a constant times the antiderivative of that function. The constant can be brought out front of the antiderivative sign, and likewise can be brought out front of the derivative sign, and the definite integral sign too. Now the product rule was a little more complicated for derivatives. It wasn't just the product of the derivatives. So the derivative of a function f times g is f of x times g prime of x plus g of x times f prime of x. That is, the derivative product is the first factor times the derivative of the second factor plus the second factor times the derivative of the first. We reverse the product rule with something we call integration by parts. That says the integral of a function u of x times the derivative of v of x dx is u of x times v of x minus the integral of v of x times u prime of x dx. Or condensing the notation somewhat, that says the integral of u dv is uv minus the integral of v du. The quotient rule we see here on the left, we don't really have a direct way to reverse that, but the quotient rule can be written as a product of two things, and so the parts rule, integration by parts technique, often works there. Now the next one is the chain rule. Now the chain rule says the derivative of f of g of x is f prime of g of x times g prime of x, or you can do a substitution. The derivative of f of u is f prime evaluated at u times the derivative of the u. The technique that we call substitution is the reverse of the chain rule whenever we do this for antiderivatives. And really, just like the chain rule, we did a substitution, u equals something. We're going to do the same kind of substitution, in fact the exact same substitution, when we reverse this to do the technique of substitution. Now a couple of special rules exist for definite integrals. The definite integral from b to a of f of x dx is the opposite of the integral from a to b of f of x dx. Also, we see that the integral from a to c of f of x dx plus the integral from c to b of f of x dx is the integral of a to b from a to b of f of x dx. So, the property here on the left says that if we reverse the order of our limits, we put an opposite sign in front of the family of antiderivatives, or in front of in front of the definite integral. Then over here on the right, it says if we want to find an integral from a to b of f of x dx, if we need to, or we find it's useful, we can break it at some value c, perhaps in between a and b, although this doesn't require c to be in between a and b. That's where it's useful. Break it at some value in between, and we can break it into two definite integrals. This is useful, for example, when f of x is a piecewise defined function and it has one formula from a to c and a different formula from c to b. That can be useful. Now, how all of those kind of rewrite in terms of other integrals or antiderivatives. What about some very specific ones that we can do? Well, the derivative of a constant is 0, so the integral of 0 is a constant. The derivative of u to the n is n times u to the n minus 1 du. So the antiderivative of u to the n is 1 over n plus 1 times u to the n plus 1 plus a constant. And that works as long as the n is not equal to negative 1. If n is equal to negative 1, you're finding an antiderivative of 1 over u du, which of course is just the derivative of Ln of absolute value of u. So since the derivative of Ln of absolute value of u is 1 over u, the antiderivative of 1 over u du is in fact Ln absolute value of u plus a constant. So the derivative of e to the u is e to the u du, so the antiderivative of e to the u is e to the u plus a constant. The derivative of b to the u, in general, where b is a constant base, is natural log of b times b to the u, times the derivative of the u. And so the antiderivative of b to the u du is 1 over log of b times b to the u. Now we can prove all these, but the proofs are almost one-liners. They're very simple. All we have to do is take the derivative of what we come up with for our answer and show that it must be the thing that we're integrating or finding the antiderivative of on the left side. So we want to prove that the antiderivative of the sum is the sum of the antiderivatives. So this, of course, is just like the sum rule for derivatives, and of course it's because of the sum rule of derivatives that it works. We take the derivative of our answer here, and the sum rule derivative says we can take the derivative of each piece. Of course, by the definition of what an antiderivative means, the derivative of an antiderivative of f is right back at f, and the derivative of antiderivative of g is right back at g. And f of x plus g of x is our original integram. So that proves the sum rule. And all these proofs are just that easy. With a little exception on integration by parts, but it's not too hard either. The constant multiple rule says if we take the antiderivative of constant times a function, it's a constant times the antiderivative of the function for any constant c. So, take the derivative of our answer. The derivative of constant times this function is a constant times the derivative of that function. The derivative of this antiderivative is back at f. So, and we still have our c out front. And c times f of x is our original integram. So, we just proved that. Now, to do integration by parts, this is going to be the hardest one to prove, but it's still not very hard. It says the integral of u dv equals uv minus the integral of v du. And that's just a condensed notation of this. U is a function of x, so that's u of x. dv is a shorthand notation for dv over dx times dx. And similar, du is a shorthand for du over dx times dx. So what we're going to do is we're going to start by looking at uv and taking its derivative. The derivative of the product of two functions u and v by the product rule for derivatives is first times the derivative of the second plus second times the derivative of the first. So the derivative of uv is u dv over dx plus v times du over dx. So if these two functions are equal, both sides of this equation are equal, that means they have the same family of antiderivatives. So if we take the antiderivative of the left with respect to x and the antiderivative of the right with respect to the x, they must be the same. Now, first of all, let's look at the easy side on the left. The derivative, if we take the antiderivative of the derivative of u times v, then of course what we get is u times v plus some constant. On the right, however, we have a sum, and we just proved that the antiderivative of the sum is the sum of the antiderivatives. So we've done that down here. And now all we're doing is solving for this first antiderivative here. The antiderivative of u, dv over dx times dx, by subtracting the other antiderivative from both sides. Now, what happened to the c? Well, this still had the plus c from here, but then there was also a c from this integral. And or antiderivative. So what we would do is just combine those c's together. It's still some constant, and it's arbitrary, so you end up getting all real numbers for the constant anyway. So we can kind of leave that off and assume that that's going to come when we actually do this antiderivative here. And so that proves the result we want to do, and then the notation at the top is just a simpler condensed notation. So this is how we reverse the product rule. I'm going to consider this a standard technique because it reverses one of our standard basic rules, the product rule, but it's going to be the most advanced of the standard techniques. A lot of people would consider this the most simple of the advanced techniques. but I consider it a basic technique, and I'm sure to always cover this in courses like Calculus 1 and Survey of Calculus, but of course it comes back in Calculus 2 and beyond as well. Now look at some of these other rules. The zero rule, the antiderivative of 0 is a constant for an arbitrary constant. Why? Because the derivative of the constant is 0. That's it. That's the whole proof. The constant function rule says the antiderivative of a constant is that constant times x plus some other arbitrary constant c. So why do we know this? Because the derivative of ax plus c is a. That's just the derivative of a linear function. And now the power function rule. For n that's not equal to -1, look at the derivative of 1 over n plus 1 times x to the n plus 1 plus c. Of course, we always have this derivative of the sum is the sum of the derivatives, and the derivative of c is 0. So that part just goes away. So it kind of shows you why you have to have that c there, because any c that you put would be an antiderivative if the right thing is here in front of it. Okay, so when we do the derivative rule here, we take the old power, n plus 1, times the coefficient. Well, that just cancels out to 1. And then we subtract 1 from the power, and we get x to the n. Now that rule works just fine unless n is -1, and then the whole thing to begin with here, or to end with over here, is dividing by 0. That's no good. But look what happens when you let the power be -1. Well, we claimed that we're going to get the logarithm here, so let's take a look at that. The derivative of log of absolute value plus c, again, the derivative plus c is 0. The derivative of log of absolute value of x is 1 over x. Well, 1 over x is just x to the -1, and that is x to the n when n is -1. So in either case, the normal case for the n not equal to -1, and the logarithm case where n equals -1, when we do this, when we do the derivative of our answer, we got the original integrand x to the n. So notice that in general, when we're taking an antiderivative, we're reversing the process of derivative. So like any inverse operation or inverse relation, we're doing the opposite steps in the opposite order. So when we take the derivative, what do? We first take the old power, pull it out front and make it multiplication. Or if it has a coefficient, just think of it this way. Take the old power times the coefficient. And then we subtract 1 from the old power to get the new power. Well, if we do the opposite steps in the opposite order, when we want to take an antiderivative, we first add 1 to the power and then divide by the coefficient by the new power, or multiply by the reciprocal of the new power. So it is the opposite steps in the opposite order. And finally, one more basic rule is the exponential function rule, and it says the antiderivative of b to the u du is 1 over natural log of b times b to the u plus some arbitrary constant. And again, all we have to do to prove this is take the derivative of our answer, that family of antiderivatives, and show that we get the integrand. And all we use there, of course, is the exponential rule for derivatives. And of course, we're always using the sum rule and the derivative constant rule. We'll use that to say that derivative of c is 0. And the derivative of 1 over ln of b times b to the u. Well, 1 over ln of b is a constant, so we factor that out front. The derivative of b to the u is b to the u times the natural log of the base. Well, that's ln of b times the 1 over b cancels, and we get b to the u, which is our integrand, and that's exactly what we expect it to be. So in the next video, we're going to look at some very basic examples of using these rules to find some antiderivatives. Okay, and we're also going to we'll find the family of antiderivatives. We'll find a specific antiderivative given an initial condition, and we'll also compute the exact value of definite integral using the fundamental theorem of calculus, and we'll use our graphing calculators to check our answers. We'll compute all these things by hand, but then we'll use our graphing calculators to check. And we'll do some of that in our next video.